Good afternoon. I'm Mark Lewis, the Executive Director of NDIA's Emerging Technologies Institute. And it's my pleasure to welcome you to our next in a series of our Technology 101 webinars. First, thank you to all of our attendees for your support of this series, for the support of NDIA and ETI, and especially for joining us for today's webinar, which is entitled Blockchain 101. It'll be presented by Dr. Ian Taylor. This webinar is part of our ongoing Tech Thursday series, in which we attempt to distill complex technologies into an introductory webinar that's focused on the science and engineering of various defense technologies. Let me begin with some administrative remarks before we get started. First, all attendee lines are muted. However, if you have a question during the webinar, you can submit your question to the question box in the webinar panel that will be on the right side of your screen. We will do our best to get through all the questions during question and answer. No guarantees, but we will certainly try. Also, please note, we are recording today's webinar for NDIA, for Women in Defense, and for NTSA members who are unable to attend, or for any member who wishes to review the material that you're seeing today, albeit at a later date. And within the next few days, we'll post that recording along with slides and some of the answers to the questions and answers session that we conduct for your review. Without further ado, allow me to introduce our very distinguished speaker today, Dr. Ian Taylor. Dr. Taylor is a research fellow at the Acquisition Innovation Research Center, AIRC, at the Stevens Institute, and he's the CTO of SIMBA chain. Dr. Taylor is also a research professor who's currently on leave in the Department of Computer Science and Engineering in the University of Notre Dame. Dr. Taylor obtained his PhD in computer science studying neural networks applied to musical pitch, designed and implemented the data acquisition system and Triano workflow system for the Geo 600 gravitational wave project. So really quite a myriad of applications within the realm of computer science. As you can gather by the title of this and the topic of this seminar, Dr. Taylor is someone who specializes in blockchain technology, works on open access, web dashboards, APIs, workflows. He's published over 180 papers, 3 books, won the Naval Research Laboratory Best Research Paper Prize in 2010, 2011, and 2015. He acts as the general chair for the Works Workshop on Workflows at the annual Supercomputing Conference. And in 2018, he was on ICO Alert's list of the top 40 blockchain influencers. So Dr. Taylor, thank you so much for joining us. Thank you so much for providing us with this webinar. We're all eager to hear what you have to say. And over to you.
Thank you very much. Happy to be here. So I think you pretty much covered this slide. Can you all hear me okay, just to check on that?
Yep, thanks.
Okay, all right, perfect.
Volume is good.
All right. Okay, so today I was asked to provide an overview of blockchain, an introduction. Start with an introduction and kind of looking at the areas of blockchain that are appealing and how they might be applied to different applications. And then I'm going to go through some of those applications that are out there and that we're involved in also. So it's a range of kind of different applications. I'll also kind of talk a bit as I'm going through this about the different some of the different use cases that kind of give analogies to what we're seeing out there in more of the public sector in blockchain. So I thought I'd start off with a few quotes. Gary Gensler, he's the chair of the Securities and Exchange Commission. This is from a Coinbase Coinbureau article, and this quotes kind of a number of technologies, one of which is blockchain. Though we're still in the early stages of these developments, I think the transformation we're living through now could be every bit as big as the internet was in the 1990s. That's pretty kind of interesting statement for that level of person. Another person's here, Mark Andreessen. He basically was one of the co-authors of Mosaic and co-founder of Netscape, and then thereafter he formed a venture capital firm called Andreessen Horowitz, who are very one of the kind of most successful venture firms out there. And he said, I think this is a foundational technology change, a new architecture for building an entirely new generation of computing systems. We have become convinced that Web3 and blockchain and crypto is foundational. It's a big hill though. It is as foundational as an architecture shift as ones from the mainframes to PCs, from PCs to the web, and from web to mobile, or traditional software to AI. It's a fundamental shift, and building this out will be a 25 to 30-year process. That's kind of an interesting observation. They've invested a lot in Web3 and blockchain applications, and it seems like a very sort of a compelling kind of thing to say about this technology, which is pretty new. It's Bitcoin has been around since 2008, but really more blockchain centered applications, and there's a massive difference between crypto and blockchain applications. They're related, of course, but there is a big difference there, which I'll illustrate. This is it's a very kind of recent thing, since 2015, 2016, really, where that piece of it started taking off. Okay, so let's start off with what's the difference between a centralized ledger and a distributed ledger. So in a centralized ledger, you can imagine like a bank is basically a custodial for all of these records. It is the place that everybody needs to go to reconcile their own records. So different banks might go to this kind of central bank that holds this golden record, and they need to reconcile their transactions against this source of truth ledger that this one bank owns, and is acting as a broker for all of these other banks for. This is this is a system that has worked for many years. It is it does rely on the trust of that central party, and it also relies on the fact that that central party is consistent, and they can reconcile the transactions with all of the people they interact with. A distributed ledger, on the other hand, is not like that at all. It's basically a shared ledger, and then each node in the ledger has some level of access to the ledger, and that distributed ledger is an umbrella for other technologies like blockchain. Distributed ledgers, the kind of more theoretical, well, not more theoretical, but more kind of a generic version. So in order for this system to agree, they don't have a single point to go and kind of synchronize with. So what they need to do is they need to come up with a way of collectively agreeing on how data comes into the system, how it's successfully kind of added to the ledger, and how everybody has access to that. And this is generally in these types of systems called achieving consensus, and there's various ways of doing that, and we'll touch on some of those. So if we go through distributed ledger technology, a DLT, well, the term actually describes the technology. So distributed refers to a decentralized rather than centralized nature of the system. A ledger represents a database of records, and the technology defines the protocol on how these different distributed nodes synchronize the data as a decentralized database. And this, one of the key attributes is that must be done in a way that's as decentralized as possible. So in other words, without a central authority to regulate it or control it. So blockchain is a DLT. It's an opinionated DLT that does things in a specific way, and it specifies how data is organized. And it's basically, the name blockchain comes from the idea that blocks are added to a chain and they're tied together using cryptographic algorithms. We'll come back to that in a bit. But essentially, the database is not managed by a person. Instead, everybody in the network gets a copy of the entire basis, and old blocks are preserved forever while new blocks are irreversibly added. And this kind of idea that everybody has a copy is specific to blockchain, and how the blocks are tied together is also very specific. But it's also an example of a distributed ledger technology. And there's many other distributed ledger technologies that do things in slightly different ways. The blockchain is really the most popular version of that. So if we go back to Web 2, the key features Web 2 enables, enabling the disruption in the TCP/IP kind of era, is mass communication, Twitter, Facebook, a whole bunch of kind of different systems there that enable that kind of communication. Standardization, so W3C is a good example of that, including interoperability. There's standards for how people can interoperate, and there's also services like Stripe and so forth that provide some level of interoperability in specific areas. Another thing that Web 2 enabled is the lower cost of IT services and features, through the invention of cloud and the adoption of cloud computing, the availability of dynamic, CPUs and so forth, and that kind of thing became possible, and APIs were enabled to just enable the dynamic creation of those and scaling and so forth. So that's in the Web 2 era, and they're all very positive things. Some issues with that approach is, and this comes up over and over again without even talking about blockchain, but the idea of centralization, this data being owned by specific entities. Also, this results in data silos. So when you have a data silo, it's easier to attack because there's one entity that holds it rather than many. It's not owned by the creator of the data. In other words, if you don't pay a fee, you are the commodity. So if you enter data in a system that you're not paying for, then generally the kind of trade-off there is that that data can be used for other purposes and it can be resold, and that's seen across the Web 2 space. I wanted to touch on centralized versus decentralized. So in the centralized case, if a single copy of the ledger were changed by any means, data or wealth would be lost unfairly, right? There is a custodian of this data. There is an entity that people trust to keep that in good order. With a decentralized ledger, nobody has to trust anybody else. In the extreme case, and that does vary, so you have the public ledgers, which that is much more true. You don't trust anybody in those ledgers, and those algorithms work very differently to the more private blockchains, which has more trust, but they still have a consensus to basically have those participants agree on this consensus. So trustless environments is assumed from the beginning with a decentralized ledger, and it isn't in a centralized one. So if we go through how blockchain works, imagine Peter wants to send a token, call it ETH, that's Ethereum, to Paul, and I'm using a token as an example here, but I'm going to delve into how this is much more generic than just passing tokens around a network. This is one of the most simple use cases, I think, of blockchain. But Peter wants to pay Paul an ETH. So what happens is Peter generates a transaction, and that transaction is signed, and that signature is generated digitally from their identity. And in the crypto, in the blockchain world, that is really their wallet. And technically speaking, a wallet is a synchronous pair, basically. So it's a public-private key. And the way you sign a transaction is you essentially use the private key to sign a fingerprint of the data that you're putting into the system. And that enables somebody to decrypt that fingerprint using the public key and compare that fingerprint with the original. And if those match, then it must have been put on by Peter. So Peter is digitally signing this as it goes into the system. So he is signing something that sends an ETH to Paul, but a transaction just stores the data, and I'll come back to how that mechanism of transfer happens. So this transaction goes into a block. There's many transactions in a block. They're chunked up. It depends on the system. Some have thousands of transactions, others have 10 to 20. It depends on the system. That goes into a peer-to-peer network. The way that's reconciled is there's a validation that is performed, and that's through this consensus protocol. And they range depending on the network. So like proof of work has everybody solve a puzzle, and then other ones, proof of authority, would be more used in a private network, and they don't use kind of those calculations at all. But that network comes to a consensus. They agree on that block. A miner puts that block onto the chain, and that block is tied with the other blocks in the blockchain. And essentially, the simple way of looking at that is that this block contains a fingerprint of all of the other blocks. So if any block is removed from the blockchain, then that fingerprint, you can't generate that again because a piece is missing. So that enables this system to be consistent and to grow and to work correctly. And that's complete, but it's not quite complete, because that's just adding a transaction to a system like this doesn't make that token move from one person to another. What makes it move is a smart contract. And a smart contract basically is a programmable means of performing an action. In this case, the action is quite simple. It's remove one token from Peter's wallet and add one token to Paul's wallet, but you also need to do checks. Does Peter have one token to begin with, and so forth. So there's a number of rules involved in that, but it's quite a simple thing. So a smart contract is actually programmed, and then it's deployed into the blockchain, so it's non-changeable. So when you're transacting and you're sending that token, that contract Nobody's hacked it. Nobody's changed the logic. You know that you're entering into a contract that's what they call contracts, that is sending that token from one person to another, and you're agreeing to that by signing that that whole process. Smart contracts can include chains of events. So these are events that basically the conditions that need to happen for this to work. In the case of the token, it's just simply, you know, those simple things. Is there a token to transfer? Yes, okay, transfer the token, but there's some other rules associated with it. Smart contract languages are like regular programming languages. They're like Solidity, which is one of the more well-known ones. It's very similar to things like Java and C, but it's more constrained. So you can't, you know, you can't do multiple things like call websites or whatever. It's kind of the logic is constrained and run within the system, which is, you know, on chain, and that contract is executed within that environment, not outside that environment. And then once this happens, the execution and value transfer happens, so that operation happens. And then with the settlement, that after that's happened, after that contract is executed, then that data is written into the chain, and that is a record of that's happened, and it's a record that the smart contract did what it was supposed to do also, if it succeeds. So that's how it works for smart contracts. And if you look at that, what are the advantages there? Well, Peter can never deny having sent the token to Paul, because he signed that transaction, and that signature is only belongs to Peter, so he can never deny that. Paul can never deny having received the token, because there's a public record on chain that says that went into Paul's wallet, and Paul, you know, cannot deny that ever happened. And the consensus mechanism pulls this stuff together, but it also ensures there's never a double spend. So you can't execute that contract twice and have two tokens. That's not that's something that the blockchain kind of ensures that will never happen. But this is just a very simple use case, cryptocurrency. So forget about cryptocurrency now, and let's talk about other things. And if you talk about other things, especially in the DoD, you know, imagine this representation, this tokenization represents other things. Imagine it represents a wing for an F-18 aircraft, and you tokenize that. Well, there's a token representation of the wing that binds to a NIN and a serial number or whatever. So you could track that wing across the supply chain as it moves around, and each of those transitions from one entity to the other is as simple as transferring that token. It's a secure means of transitioning that entity across the supply chain, and that, you know, that is a very kind of a nice way of tracking supply chain, and it's a secure way of ensuring that is not being hacked across that. But it goes further, so you can then, you know, track sub-assemblies in that way. So as, you know, the wing is being assembled, there might be sub-tiers that, you know, work on certain parts of it. That can be tokenized also, even down to the production of those sub-assemblies. And that transition of that sub-assembly can also be tracked along the route. And that is all done within an environment that nobody can change the data. You know, the source of truth is coming directly from the manufacturing process, and you can track all of that all the way across the system. And I think that's the level that, you know, I think about things. I'm not really a big sort of participant of cryptocurrency, but I really think that the technological advantages of that are very interesting for a lot of use cases. So I'm going to quickly delve down into these features, and then we're going to look at some use cases. So blockchain has this immutability. Going from the left here, it has the consensus that has which is the mechanism where the network agrees. It has the smart contracts that can enable the specific logic to be applied when those transitions take place. It has a complete provenance trail because everything is recorded forever. So you have this information right back to the origination of the asset, and it's secure. So, you know, each transaction is digitally signed, so you know it's identifiable in the sense you know exactly where it comes from. And every transaction could be identifiable to a wallet within systems that are more sort of private, as they say, which is more sort of a consortium-based network. So put this together, well, you know, this technology represents for the first time really the ability to transition any digital or even physical asset from one entity to the other without a central coordinator being involved. And while you know, cryptocurrency does this for monetary value, there are lots of other use cases, and there's a whole ecosystem which I'll go to in the next slide, which kind of covers various applications, you know, from from supply chain, healthcare, legal and government to secure and optimization of business processes. NFTs are another example. They're another type of token. And if you forget about the NFTs on OpenSea and things like that, but think about how they represent, real assets in our world, this gets very interesting as well. And, so an NFT can inextricably be linked to a digital file, like data files or IP, for example. It can represent IP and how that IP can be used and transferred. That's an interesting use case. But it could also be bound to physical assets using, RFIDs, QR codes, whatever. There's various means there of binding the physical to the digital. And once you have that, then you can track use NFTs as a way of representing those on chain, and then you can transition. You can move these NFTs, you can move these physical objects between one entity and the other, and then that becomes very interesting. So this is the ecosystem. On the left, these are the projects that are represented in the graph there, which this circular representation here, which is an interest in, and I put that there just to show the sheer kind of activity in this area. And then there's the blockchain ecosystem, which really has a number of advantages, which I'll briefly go through, which are useful in various applications, and I'll touch on use cases that kind of hit on those. So the blockchain features here on the top level here, immutability. So blockchain is immutable, it's non-changeable. So it provides a single source of truth for any data you put on the system or any transition of assets that you choose to move around the system. Transparency, blockchains provide transparency publicly, cryptocurrency is an example of that. Private chains provide controlled transparency across a consortium of entities. And you can control who has access to the information to some degree there's various blockchains that offer that kind of level of authorization. But that is much more flexible within that environment. And that's a very interesting kind of area that is growing rapidly in blockchain. Digital freedom, so no third party that control the data that is stored. No data. The data isn't owned by the data is owned by the network, not by a single entity. And then the concept of decentralized services. This in my mind is really sort of about the smart contracts, and it's not about kind of operating in a decentralized way so much. It is to have a smart contract that is written into the blockchain, and therefore it cannot be changed, and you have this operating in this decentralized system, which provides kind of a deterministic and non-hackable means of applying logic to whatever application you want to apply it to. Efficiency, there's no third party involved, so processes, and also through the use of smart contracts, processes can be automated in a trusted way, and transactions can therefore, because that trust is built in and there's less interaction going on, they can reduce those, that kind of those scenarios down to seconds rather than kind of days and weeks to complete. And inexpensive, with no centralization, there's no need to have a custodian for the data. So there's no need to pay and manage a central entity to keep all of this. It's more of a collaborative, which leads to network, which leads to efficiency and less paperwork. So there's a number of applications this is quite interesting and useful for. So siloed data repositories, minimal system trust, process interdependencies, where you want to connect things together in a way that you want deterministic logic. You want that logic to be kind of trusted. Multiple data writers where multiple people are accessing the system at the same time. Blockchain is very good at kind of ensuring that the ordering of those and the consistency of those, there's we go through the consensus mechanism that is ensured. And then shared rules. These shared rules can be agreed on by consortium and implemented through contracts, which can be known and trusted and deterministic, so that they're going to work the way they're going to work every time they're used. And then the last thing I'm going to touch on really is this concept of public or private. And private is kind of, I don't think it's a great word for it. It's more enterprise or consortium based. In a DoD scenario, you want multiple participants within the DoD to participate in a cost efficiency exercise, for example. So yeah, it's private because it's in the DoD, but it's more of a consortium based network where those participants are really agreeing on the rules about how data is coming into the system and how it's transitioned. So public ledgers are generally anonymous. And that I put that in inverted commas because it's anonymous to the extent that the identification is by wallet. It's not particularly mapped to an identity that maps to a person. There are systems, however, even on those public networks that, chain analysis, for example, and so forth, that can take those transactions and figure out who those wallets belong to. So it is questionable whether it's really anonymous. But the idea is, it's you just need a wallet, a public-private key pair to participate, and that's how you're represented. On a public network, it can require proof of work mining, which is very energy inefficient. The more recent networks and the more efficient ones use proof of stake, and they're much more scalable. Some of the proof of stake networks, can operate 5,000 to 60, 70,000 transactions a second, and this is based on the concept of people staking money or currency into the network, and they would lose that that stake if they misbehave. So it's based on partial trust through that kind of mechanism of not reward, but kind of removing the reward or the stake in the system. And then private enterprise or consortium networks, they're not anonymous. Generally, each entity and person is known beforehand and agreed. You're basically creating a consortium. And this can map to an identity, and it generally does. So in an enterprise environment, you have existing users. Those existing users want to they want to benefit from this new technology, and therefore they want to connect to a system, right, that enables them to use this. So typically there's a map in there from an existing identity through to a wallet, which identifies them on the blockchain or the ledger that they're using. So for example, in the DoD, that might map to a CAT card. So you might log in through the CAT card, and then the system could basically generate or or map to a wallet that identifies you uniquely on the underlying system. And on these enterprise networks, typically the algorithm that's used is proof of authority, which is based on this idea that the entities are known, we're participating, we're collaborating, but we want to keep this a decentralized process amongst that consortium. So it's less, you don't need things like proof of work for that environment because the participants are somewhat trusted in the first place, but you do need to ensure that no single entity is in control. Okay, so just a couple of surveys before we jump into the use cases. Just look at the time. Okay, I'm good. So this is a Gartner Trend Insight report from 2018, and it was just agree or disagree, blockchain would disrupt my industry, just based on kind of the executives at that level. Automotive was one of them that they felt this could change, and I'm going to talk about car titles later on. Oil and gas, life sciences. You can see these. There's various kind of sectors, including the public sector, which has some degree, like 46% of those folks thought that this technology was interesting and useful to solve some of the use cases. So that's interesting perspective. Another Deloitte 2018 report, companies care about blockchain was the question. Critical was 43%, important and relevant 50%, and not relevant and unsure 7%. So again, just the general consensus is that this technology is interesting and useful. It doesn't replace everything. It's part of a solution, not the entire solution in many cases, but it does have those features that it exhibits do fit into kind of like a, overall picture of some use cases. And then blockchain is growing rapidly. This is a Gartner report that was released, and they estimate 360 billion by 2026, 3 trillion by 2030 as this really gets widely adopted. And 10% of enterprises will be using it in some form or the other, even this year. But there are barriers to entry. This is it's more than 100% because people could choose multiple things. But it gives you a feel, some people feel it's unproven. Some people feel there's no compelling motivation. There's a piece that lack of in-house skills. So how do you adopt this technology in the first place? Security is another worry. And implementation is, probably feeds back into lack of in-house skills. How can you get this implemented within your environment? And then of course regulatory issues, they impact everything that can happen, more in the public sector maybe than the private, but still they will impact the technology. Okay, use cases. So I'll spend the last 10-15 minutes on 3 different use cases that I'll just go over just to give you a feel of what can be done. And hopefully one is from kind of the more public sector, another is private sector, and the third is the DoD use case. And I just wanted to, each are thought-provoking, I feel, in one way or the other, and they just show how the technology can be used. So, so one of which, car titles, this is interesting. We know about this project. We're sort of on the fringe of it, but there's other Spruce ID, for example, are involved in it, and Tezos right now. But the idea here is that car titles are they're implemented differently on in every state, of course, but they're generally based on kind of systems that are prone to error. It's very difficult. Some states, like I'm in Virginia, and it's paper titles. For example, and you have to register, and Florida has digital titles, but they have different rules. So, but the ability to, for vendors and just the general public to sell cars there's a lot of issues there in terms of there's fraud, there's issues in terms of people losing the car titles. We were talking to some folks in California, and they said there's 18,000 dealers in California, and each dealer employs 2 people just to kind of understand whether the titles that come into their showroom are authentic or not. So that's quite an overhead there. So if you take that idea of a simple idea of just car titles, and you represent that as an NFT, that provides an interesting kind of scenario there, because now you're representing the NFT as a title. The idea of the NFT could be the VIN, for example, which is unique to the particular vehicle. And then selling a vehicle or transferring the ownership from one person to the other is simple as transferring a crypto token, or a cryptocurrency or whatever, or an NFT or whatever that you're transferring in other means. And that has all those features that we talked about. So it's unhackable, it's a way of transferring it without an intermediary. And this could all be transparent and available immediately to the DMV. The DMV is working on these ideas. They're quite early at this point, but they're very interested in this kind of type of technology. So I thought I'd just say a little bit about that. So customer problem, there's lots of manufacturers, dealers, insurers, lenders, consumers all involved in this process. It's often a tedious process with many manual steps, including title verification. It's slow for that reason. It's expensive. There's also lost titles, nefarious intent. In terms of salvaged vehicles is a big problem, for example. Errors, so papers misrepresented, personal information, vehicle history, and so forth. That is all sort of stored across multiple systems and paper and so forth. So that becomes an issue, and it's expensive for all of those reasons. So blockchain really has some interesting advantages here. It's speed. It's much faster than the existing system, because you can transfer property very fast and securely using NFTs in a peer-to-peer network. It's pretty much instantaneous. If you're working on, say Tezos, there's finality there within a second or something. So it takes a second to transfer an NFT rather than, however long it takes depending on the state you live in. It's 100% automated, and it's not just the transferring of that. There can be rules surrounding that transfer. So you can have a transfer conditional, on the lender's the lender being paid off beforehand. That could be part of the smart contract process, not in a crypto sense, but in a basically a contractual sense. So they can participate in the system, and then once those activities have been done, those transactions can be signed by the lender, for example, which releases the lien on a title, which frees the title up to transfer an NFT. So those processes could be made much more efficient through those means. And it's decentralized, so there's transparency and efficiency, no intermediaries. And there's also full provenance right back to the certificate of origin for a car if you do things this way, which is very, very easy to prove and know that that's never been hacked. So you would never buy a salvaged vehicle unknowingly in the future if you adopted something like this. This kind of applies to various industries as well: carbon credits, real estate, medical records, IP and patents, academic credentials, ticketing, and so forth is some other examples of this how NFTs could be used today in different applications. Another example which SIMBA chain has been involved in, actually SIMBA chain and the University of Notre Dame was involved in this use case initially, and then SIMBA kind of built it out. And there, this is a really, I've met these farmers and I've been to Ghana to meet them. This project has been running in production now for a year and a half or so, a little bit over a year and a half, October 2020. I think it went live January 2021 in production. So we've been tracking this coffee for all this time, and this is you know, the benefits for talks in this exercise. They already had sustainability efforts going on in the company, and they already were working with these farmers in this region to try and cut out the middleman in the supply chain, which was challenging in itself, and also to provide transparency and visibility to their customers. That last piece they couldn't really achieve because they did a survey with you know, their customers, and they asked if you know, sustainability and some details about that, if they wrote that on, you know, the coffee in this example, on the packets, would they believe them? And 76% said no. So they needed something more, you know, more automated, more trusted, to track this coffee right from the farm all the way through to their 200 and so restaurants they have across Mexico. And this kind of enables not only the tracking but new business models, and I'll talk about that a little bit after I go through this. But essentially, this is what happens in this process. So the farmer works in these mountains in Takana. They bring in bags of coffee. They're generally about 100 kilos. They bring them into the cooperative, which is coordinating this process. That bag of coffee is tested for the weight. It's tested for humidity and other parameters. And a QR code is generated and put on that bag of coffee. So these are the beans coming in, right? They're called green beans at that point. And then those beans go to the desheller. So there's another transaction on chain. So that initial transaction when they come in, all of that those details are stored. Then it goes to the desheller, and when a transaction goes to know that it's left the cooperative to go to the desheller. When it comes back from the desheller, another transaction happens, and this time they reweigh the coffee, and they take the humidity again. So you now have physical characteristics that bind to a QR code, that bind to a non-reputable mechanism underneath that says exactly where that coffee came from and what physical attributes that were characterized by that coffee at the time that happened. So you couldn't, you know, if you wanted to hack this process, you wouldn't be able to do it. You'd have to essentially copy the barcode, and then you'd have to get beans that after they were deshelled were exactly the same weight and humidity that those original beans was, even to, you know, beans were, even to kind of, you know, produce counterfeit coffee in this system. So this tracking continues. It goes from the desheller to the roaster. The roaster, you know, roasts the coffee, it grinds them up, and it puts them into packets, which go into boxes, 20 boxes as packets in a box, and that has a different barcode which binds back to the original QR code. After the warehouse, it goes to the warehouse rather, and then it goes to the restaurant. So the result is now any restaurant that receives any of this coffee, you know exactly where it comes from. But not only did we do that in this use case, it was also possible to have different grades of coffee because they were tracking it through the system, and the roaster had to, you know, keep to that quantization of how the, you know, coffee came into that roaster. They were also able to separate good coffee from excellent coffee, which the farmers knew there was a difference between different types of beans that they grow. So now they're tracking those two different types of coffee, and they're monetizing those in different ways in the restaurant. So now more revenue goes back to the farmers to provide more sustainability. Just to give you an idea, like before this started, those farmers would be paid $60 a bag, and after this process, right now they're getting paid $250 a bag, and that's a massive increase. These communities are around about 20 families, and there's reverse migration happening because, you know, there's actually sustainability in this process. So here, I think I've been through most of these, but, you know, the ability to track that coffee supply chain really across these different entities was one of the issues, and also to prove out sustainability and to eliminate counterfeit coffee. So why blockchain? Well, you know, this has an unchangeable underlying kind of ledger. that all of this information is changed on, that binds to the physical characteristic, that proves, that no other bag of coffee could go across this supply chain this way, because every bag of coffee is slightly different weight and a slightly different humidity. So we have this kind of unique binding between the physical and digital. And the traceability to farming sources increased production from 11 to 25 tons, as well as part of kind of farmers getting more involved in this process and realizing this was a better way of engaging in the industry. And if you think about this, in terms of the DoD, well, think about additive manufacturing. Again, there are physical characteristics here that could be, tracked, and you could represent an additive manufacturing component as an NFT or some other means on chain to track it. And then the last use case is aviation, and I touched on this a little bit earlier. But the ability to track and trace each part of an airplane is an interesting use case, which is going on in the DoD to some degree through this project VIPART, which finished a few months ago. And just to kind of give you an idea of what happened in that project, so essentially it was a collaboration between Boeing and NavAir, and really what they were doing is tracking F-18 wings. There's various in and outer wings. There's like 8 different varieties on 2 different aircraft or something, and tail hooks. So the way that worked roughly, it was a Hyperledger Fabric system that was connecting from Boeing into an environment that NavAir had access to, and Boeing were interfacing to that Hyperledger Fabric network, and they were providing, based on the POs that were initiated from NavAir, the Boeing was tracking every single part, in terms of the wings that were ordered, and they were providing progress updates on those wings. So now Boeing, every day they query their internal systems, they figure out what the progress of that wing is, and they give a percentage, back to that particular PO. So now, there's visibility across across the supply chain, and and then in the same project, they also went down to a second tier and provided information on the progress of sub-assemblies at a very high level. And there's other efforts going on now to expand this to more, entities than Boeing, and having that run across many more parts. And this kind of this is steps, towards the vision that I painted earlier, which is, if you could use NFTs or some other form of smart contract to track these parts during production, now you have information available to you that you never could have before, because that interaction was never possible previously. So this, I'm just wrapping up to turn over to questions. So the customer problem there, lack of visibility. NavAir didn't have insight into these different wings that were being created for this use case. Also, the ability to collect synchronous data across these different systems, across these different tiers of the supply chain, was just not possible, and also a missing end-to-end view of the maintenance, repair, and overhaul in circumstances where this was part of a overhaul of an aircraft. And blockchain provides this secure and trusted means and unchangeable source of truth that both parties trusts. Boeing wants to provide data to NavAir in a way that cannot be hacked by a third party, right? An adversary, for example. It also wants to ensure that data isn't changed by either party. So this is a trusted flow of information that really kind of helps the underlying kind of use case. Okay, so that is what I wanted to get to, so I'll turn it over for questions.
Ian, wonderful. Thank you so much. Incredibly informative. You covered a wide range. I really appreciate that. And to reflect that, we actually have a number of very good questions. And I'm going to try to take them pretty much in the order in which they came. They run from the detailed to the profound. So okay. First question is, does every transaction have to be approved, or can there be consensus agreed by all nodes of the blockchain each and every time?
So, yeah, I mean, a transaction being approved is part of the consensus process, and it depends what you mean by approved. So that there could be situations where, I mean, generally the consensus algorithm is really sort of agreeing that these transactions exist, and they agree that those come into the system. So, yeah, so I think then the answer to that question is it depends on kind of that definition, but generally that is the case. They are approved and part of the consensus algorithm.
Understood. Next question. Can miners collude to change the past in a public blockchain?
Well, to collude and to change that, if you're talking about proof of work, they would have to collude and become more than half of the network. So they would need to control more than half of the. Oh, can I stop sharing? Sorry. Okay, is that better?
Yes.
Okay. Yeah, so they can do if they gain more than half the network, and this is where I go back to how decentralized this system needs to be. So in public chains like Ethereum and Bitcoin, where there's no trust, you need to have many participants and have them incentivized to participate in that process. So miners get rewarded every time they win a competition or they get selected to mine the block. So there's that incentive piece there for people to become and remain involved. And the more decentralized you can make that, the less likely that compromise can happen. But if they do gain 51% of the network, that could happen.
So it's possible, but not likely.
Not very likely.
Here's a question coming in. How does the database not get really, really large if it contains all past transactions?
Yeah, so there's various sort of ways of approaching that. So, I mean, first, what I'd say is the way, even if you look at NFTs, for example, in the specification for NFTs, they recommend that the metadata is stored off chain. And the reason is because they don't want to bloat the chain with all this information that's not critical to the actual sort of transition of that asset. So the first part of that question is they try and keep the blockchains as efficient as possible, but then you have new blockchains that are out now enable sort of much more scalability in that way. So there are chains, for example, Arweave is designed to store data, which can be bound across to Polygon, which is a layer 2 network, which is very efficient and can store more data. And then there's also kind of sharding and stuff that other networks are working on. So there's various strategies that have been discussed about how to solve that issue, but I mean, the rule of thumb is really keep the data as minimal as possible on chain to achieve what you want to achieve.
I guess we also have a related question, which is, can a chain reach maximum capacity, and if so, what happens to it?
That hasn't happened yet, but yeah, I mean that's a good question. I mean, there are different ways. I think I just answered this to some degree, but there are different ways of kind of having data, distributed in that way. So there's different approaches of how older data can be moved to other tiers of the network. There's various kind of ways of how that could be solved. Data could be archived and then reproducible in some way. So there's various kind of approaches that are out there to solve that problem, but it is, it's an issue, and but there's various solutions that have been proposed for that issue that can achieve, longevity.
So here's a question which I think contains a note of maybe skepticism. Individual asking, so how is blockchain different from a website that simply records every transaction with a timestamp?
Well, so there's several differences there. So the website is centralized. So there's several factors in that. You have to have somebody pay for the hosting of that website. You have to have somebody control this website. So that person who controls the website and the database controls that data. And also every transaction is not identifiable in that way. It could be if you build a system where people log into that system and you record that in a database, but then that database could be changed. So there is no kind of, deterministic binding, if you like, between that identity and the data. Databases don't sign transactions, for example. They don't. So databases can be changed. So I think there's many differences there. I hope that makes sense.
Yes, it certainly does. Here's a question from one of our participants asking, is there an alternative to a power-hungry proof of work for validating a public blockchain?
Yeah, so proof of work is the original sort of algorithm that Bitcoin used, and it's based on this concept that everybody goes off and solves a puzzle, and you know, when the first person that solves that puzzle, is selected as the miner that puts the block on. So that implies that you have to have a pretty powerful machine to compete, right? And interestingly, the blockchain, Bitcoin, that problem generally takes about a year to solve, but there's so many participants involved in the mining process, somebody gets lucky around after 10 minutes or so. So that's a massive, I think Bitcoin, I read, used the same energy as Argentina. Yeah, so it's very inefficient. And this is exactly the reason why, you know, other more efficient solutions have come along, right? So most recent blockchains, including Ethereum, is moving to a proof of stake model. And the proof of stake model it uses a selection algorithm and a way of penalizing people who don't behave within that environment rather than asking them to do calculations. And that is very efficient, and that's no more, you know, energy inefficient than running, you know, a simple service, right, on each of the nodes. So Avalanche, for example, uses proof of stake, and it has a selection algorithm which can resolve in two levels of the selection. It can do 5,500 transactions a second, and it's really super efficient and green. So there are alternatives there that are working really, really well in that regard.
Here's an interesting question about starting up a blockchain, and that is, how is the initial blockchain set up, then known and reviewed and assurance provided that is properly constructed and therefore guaranteeing the desired attributes of things such as immutability?
Yeah, I mean, they all work kind of slightly differently, but there's a genesis block that's kind of initiated and a trusted set of participants that are involved that kick the process off. And, you know, there have been issues where there's been forks in the blockchain for various reasons, but essentially, you know, that would be something like, you know, Bitcoin and others. Hyperledger Fabric works in a similar way, but it's slightly different. So there's various ways that can be assured, but it's based around kind of the initial trust of the participants and the process that they go through to start that blockchain.
Here's actually a question that I think is very closely related to that, which is, what's the maturity of the development of international standards that can regulate the use of blockchain technologies?
Yeah, I think that's work in progress, right? There are standardization efforts, and there's efforts kind of, you know, in the Hyperledger community, there's efforts to kind of standardize some things around enterprise use. There's also, you know, standardization processes within Ethereum. So every contract or every mechanism that is released that, you know, even like a ERC 721, which is an NFT, right? That went through a standardization process, and those contracts were validated and audited so that the functionality was peer reviewed by multiple people. So to some degree, all of this has some level of standardization, but in terms of, you know, W3C, which is a much more rigorous process, I don't think we're there yet. However, you know, yesterday, for example, no, sorry, not yesterday, the day before, decentralized identity, the W3 standard, which is great, and they're very related to blockchain and kind of solve, to some degree, the identity piece, the decentralized identity piece that can be verifiable. So there are efforts going on attempting to standardize, but it's still an early process. And, you know, smart contract standardization is a thing that a lot of people are talking about and trying to kind of set up initiatives for, but they're not all there yet. So partially, I would say.
Great. So we've got two questions with a very similar theme. The first question is, what would it take, or is it possible to implement distributed ledger technology and apply it to elections, local, state, federal?
Yeah, absolutely. I mean, there is a cultural aspect to that, and a political aspect to that, and a technological aspect to that. From a technological aspect, I think one of the things that would need to be solved there is the notion of identity. How is, you know, for an election, how would you issue an identity so that a person only has one identity? It maps kind of verifiably to their, you know, themselves, and they can't create another one. And like I said, decentralized identifiers provide an implementation for doing exactly that. So given that that technology is now standardized and could be used, yes, then a voting process could happen, which is completely non-hackable and non-changeable. So it would provide more transparency, but there's other obstacles to overcome in that arena other than the technology.
Yeah, I'm also, we've also got participants who are raising other applications. One suggests wine provenance. I like that one.
Yeah.
I'm sure there's a business there. And the other is asking about using the technology to verify Made in America claims.
Yeah, absolutely. Yeah. I think that both of those can be absolutely implemented. We were actually, I was on a call earlier with a farm from Florida, and they talked about a very similar problem. The buy local is a really big thing in states, and this particular farm had they produce their own goods, but right now the tomatoes come from another state, and that's not acceptable to the local buy local program. So how do you verify that? Well, it's very hard now because there is no process involved in that in the production of tomatoes that would enable you to do that. But if you had a standard way of recording that information, which was easily, which you could integrate from multiple farms, then you would have complete transparency of where things came from. And you could do exactly the same thing for, in the DoD for parts as well. If you could have the supply chain participate in that process, and that's the difficult part there. But there are incentives for them to do that because there's efficiencies on the company side as well. Providing that transparency. Boeing has been working in that area for a long time and sees those those business benefits of doing that. So I think that again, that's the issue there is participation. But yeah, absolutely can be done.
So we're about to run out of time, but there's a question here that I'd like to pose as kind of our last question, which is, how does a small company begin to use this technology? Do they buy software? Do they subscribe to a service? Will be built into services that they use, or all the above?
I think there's various ways they could do that. I mean, if they know what chain they can use, they can just go to that chain and code against that. They can use interfaces. SIMBA chain has an abstraction layer that is simple to use. There's Morales and various other toolkits that make it simpler to code, as a non-Web3 developer. So there's various routes there that I think people can get on board. There's also kind of tools that provide graphical environments to be able to create the business case you want to create, and have that create contracts that you can deploy without writing the code itself. So there's various ways that you can get engaged there.
Very good. Ian, thank you so much for this presentation. I certainly have learned a lot. I can tell by the flood of questions. I apologize, we did not get to all the questions because of time constraints, but that was absolutely spot on and extraordinarily informative. Let me thank the entire audience for your attendance and for your great questions. Again, we will post this recording on NDIA Connect as soon as it is available. As always, if you've got feedback about our Tech Thursday series, especially if you have suggested topics that you would like to see us cover, please email us at eti@ndia.org. And I'd also like to take this opportunity to highlight some of our upcoming events in the Tech 101 series. On September 8th, we'll be learning about Directed Energy 101 with Mark Neese, who's the from the Directed Energy Professional Society. And then on September 22nd, we'll be doing learning more about quantum computing with Scott Fletcher from the General Accounting Office. Registration information is on our website, or feel free to reach out to us again at eti@ndia.org. Thank you all for your participation. Ian, thank you once again for a great presentation. Everyone, have a great rest of the day.
Thank you. Thanks, everyone.